In this short video, we demonstrate the idea of path planning for collaborative micro-aerial vehicle swarms. We develop an uncertainty-aware planning algorithm that is applicable to vision-based MAVs, that attempts to plan paths while reducing localization uncertainty. This planning approach was developed for swarms of multi-rotor vehicles which are capable of localizing using vision. Using front-facing monocular cameras, features are extracted and communicated between the vehicles to obtain a reconstructed map, and this map is then used to perform feature tracking and localization. In order to plan uncertainty-aware paths over this localization framework, the planning algorithm is responsible for 1. Generating high-quality maps, 2. Making sure that good quality feature tracking is possible throughout navigation. Phase 1, we develop a next best view planner, whose function is to examine whether an initial map can be improved by 2 new locations. We achieve this by sampling random poses for the vehicles and describing how good or bad a map generated from those viewpoints can be. To describe the quality of reconstructions achievable from a set of poses, we consider several factors related to vision-based reconstruction as shown here, and for each candidate pose, we express these values mathematically. To solve the next best view problem, we sample possible poses in 3D space, and for each set, compute the values of these factors and express this combination as an objective function that needs to be minimized, thus resulting in the best set of viewpoints. We perform this minimization using an evolutionary algorithm called CMA-ES. Here, we show a sample result from the next best view planner. 2 vehicles start off at a significant distance from a building and are only able to create a very sparse map. When the next best view planner is run on this case, it quickly samples various poses and computes the best pair of viewpoints, close to the scene and thus potentially resulting in a better map. And indeed, this does result in a better reconstruction with a higher number of points. Now we discuss the second phase of the planning algorithm, how to plan paths after a good 3D map is obtained. In this phase, the focus is on ensuring feature visibility and tracking, and also to optimize path cost along with these factors. We use the RRBT algorithm which layers the heuristics and path cost above random sampling. This cost function is weighted between path cost and the trace of a covariance matrix. The figures show how the working of the planner changes based on the values of the weights. Here, we show a sample test case for the RRBT algorithm. Given a start and a goal state, which are both a significant amount of distance from the scene, the question is, how can this MAV fly between them while improving its localization accuracy? This is a path computed by the RRBT algorithm. It drives the MAV closer to the map, so it can robustly track more features, thus allowing it to improve the accuracy of pose estimation. We can see in this short video that when this plan is executed in a simulation, this path does result in improved feature tracking.